The Leonard P. Zakim Bunker Hill Memorial Bridge in Boston, completed in 2003, is a notable example of modern engineering and construction. The cable-stayed bridge, part of the Big Dig project, required innovative techniques and precise execution. The bridge features two inverted Y-shaped towers, each 295 feet tall, constructed using reinforced concrete. The climbing formwork system used for these towers allowed continuous concrete pouring, ensuring structural integrity and minimizing construction time. The main span of the bridge, stretching 745 feet, is supported by 116 high-strength steel cables, arrived in a harp configuration. These cables were meticulously tensioned to ensure even load distribution. Each cable was anchored at the bridge deck and tower, requiring precise calculations to maintain balance and stability. The deck itself was constructed using precast concrete segments, which were transported to the site and assembled using a launch gantry, minimizing disruptions and expediting the construction process. Maintaining traffic flow on the existing I-93 highway while building the new bridge was a significant challenge. This required a series of temporary supports and careful staging of construction activities. Additionally, the bridge had to be integrated within the city's underground central artery tunnel, necessitating complex coordination between different construction teams. Extensive geotechnical engineering ensured the stability of the bridge foundations, which were anchored in deep bedrock to withstand the weight and dynamic loads of the structure. The Zakim Bridge's design incorporated seismic considerations. Given Boston's susceptibility to earthquakes, engineers used advanced modeling to simulate seismic events and ensure the bridge's resilience. The towers and deck were designed to move independently, allowing them to absorb and dissipate energy during an earthquake, minimizing structural damage. One of the issues faced during construction was soil stability and water infiltration, which required additional measures such as dewatering and ground improvement techniques. However, these challenges were overcome through innovative engineering solutions and meticulous planning. The bridge's design also includes provisions for thermal expansion and contraction, with expansion joints made of flexible materials to allow the bridge to expand and contract with changes in temperature without compromising structural integrity. The Silvertown Tunnel in London, scheduled for completion in 2025, is a twin-bore road tunnel under the River Thames connecting the Greenwich Peninsula to the Royal Docks. This ambitious project employs state-of-the-art tunnel boring machines, each over 82 feet long and weighing approximately 1,350 tons, designed to handle the challenging geological conditions beneath the Thames, including water-bearing gravels and stiff clays. Construction began with the sinking of deep shafts on both sides of the river. These shafts provided the starting points for the TBMs and will eventually house the tunnel portals. The TBMs, named after historical figures, are equipped with rotating cutter heads that excavate soil and rock, which is then transported out of the tunnel via conveyor belts. The TBMs advance at a rate of around 33 feet per day, lining the tunnel with precast concrete segments as they progress. These segments are bolted together to form a watertight lining, ensuring the structural integrity of the tunnel. One of the primary engineering challenges of the Silvertown Tunnel project is maintaining the stability of the tunnel and preventing groundwater filtration. The construction site is located in a densely populated urban area with significant historical and environmental considerations. To mitigate this, extensive geotechnical surveys and advanced 3D modeling techniques were conducted to ensure the tunnel's stability and integrity. The tunnel is designed to accommodate both current and future traffic demands, with each bore containing 2 lanes and provisioning for future expansion. The alignment of the tunnel was meticulously planned to avoid existing underground utilities and infrastructure, requiring detailed geotechnical surveys and advanced 3D modeling techniques. This planning ensures that the tunnel can be integrated seamlessly into existing road networks, minimizing the need for extensive surface work and disruptions. To enhance the safety and efficiency of the construction process, the project utilizes building information modeling technology, BIM allows for the detailed planning and simulation of construction activities, helping to identify potential issues before they arise and streamlining the construction process. This technology also facilitates collaboration between different teams and stakeholders, ensuring that the project remains on schedule and within budget. The Waimea Community Dam in New Zealand is a significant project aimed at providing a reliable water supply for the Tasman region. The construction of this earth-filled dam involved complex engineering techniques to address the unique geological and environmental challenges of the site. The dam, standing 174 feet tall and 1,210 feet long, is designed to store approximately 13 billion gallons of water. The construction process began with extensive site preparation, including the excavation of a large foundation trench to ensure a stable base for the dam. This involved removing unsuitable materials and replacing them with engineered fill. The foundation was then treated with a combination of grouting and drainage systems to manage groundwater and prevent seepage. These measures are critical for maintaining the dam's structural integrity and ensuring long-term stability. The dam's core is constructed using impervious clay, which acts as a barrier to prevent water from seeping through the structure. This clay core is flanked by zones of carefully compacted earthfill, providing support and stability. The construction of these zones involved precise layering and compaction techniques to ensure that each layer met the required specifications for density and moisture content. This meticulous process helps to prevent settlements and maintain the dam's structural integrity over time. To enhance the dam's safety, a robust spillway system was designed to handle potential overflow during periods of heavy rainfall. The spillway consists of a concrete chute and energy dissipation structures, which are designed to safely convey excess water downstream without causing erosion or damage to the dam. The design and construction of the spillway required careful planning and execution, taking into account the potential impacts of extreme weather events and climate change. The construction of the Waimea Community Dam also included the development of extensive monitoring and control systems. These systems involve the installation of piezometers, inclinometers, and other instrumentation to monitor the dam's performance and detect any potential issues early. This real-time data is crucial for the ongoing management and maintenance of the dam, ensuring that it operates safely and effectively. The new Manila International Airport in the Philippines is an ambitious project designed to alleviate congestion at the existing Ninoy Aquino International Airport. Scheduled for completion in phases with full completion expected by 2025, this airport will feature 4 parallel runways and a capacity to handle 100 million passengers annually. The construction involves massive earthworks, advanced engineering techniques, and meticulous planning to create a state-of-the-art facility. The initial stages of construction focused on land reclamation and site preparation, as the airport is being built on a low-lying area prone to flooding. To address this, engineers employed a combination of dredging and soil stabilization techniques. Millions of cubic meters of sand and fill material were dredged from nearby areas and transported to the site, raising the ground level and creating a stable foundation for the airport infrastructure. The use of geotextiles and ground improvement techniques, such as dynamic compaction and prefabricated vertical drains, helped to accelerate the consolidation of the reclaimed land and improve its load-bearing capacity. The construction of the airport's runways involved precise grading and paving techniques to ensure smooth and durable surfaces. Each runway is designed to accommodate the largest commercial aircraft, requiring layers of high-strength asphalt and concrete. The paving process utilized advanced machinery and techniques, including slip-form pavers and laser-guided screeds, to achieve the required surface smoothness and thickness. The terminal buildings, designed to handle the high-pressure volume, incorporate modern architectural and engineering principles. The construction of these structures involves the use of prefabricated steel components and modular construction techniques, which allow for rapid assembly and high-quality finishes. The terminal roofs are supported by a network of steel trusses, creating large open spaces that enhance passenger comfort and flow. One of the significant challenges of the new Manila International Airport is integrating advanced technological systems. The airport will feature state-of-the-art air traffic control systems, automated baggage handling, and advanced security screening technologies. The installation and integration of these systems require careful coordination between different contractors and suppliers, ensuring that all components work seamlessly together to provide a safe and efficient airport operation. The Great Plains Power Station in Canada, located in Moose Jaw, Saskatchewan, is a natural gas-fired power plant designed to provide reliable and efficient energy supplies. Scheduled for completion in 2024, the project involves the construction of a 350-megawatt combined cycle power plant, utilizing advanced gas turbine technology. The construction process began with site preparation and grading, creating a stable foundation for the power plant infrastructure. This involved extensive earthworks, including excavation and compaction, to ensure that the site could support the heavy equipment and structures. The foundations for the gas turbines and other critical components were constructed using reinforced concrete, designed to withstand dynamic loads and provide long-term stability. One of the primary engineering challenges was the installation of the gas turbines and heat recovery steam generators. The gas turbines, manufactured by Siemens, are among the most efficient in the world, capable of converting natural gas into electricity with high efficiency and low emissions. The installation of these turbines required precision alignment and balancing, ensuring optimal performance and reliability. The HRSGs, which capture waste heat from the gas turbines to generate additional electricity, were assembled on-site using prefabricated components, minimizing the construction time and ensuring high-quality fabrication. The power plant's design incorporates advanced cooling systems, including air-cooled condensers, which reduce water consumption and environmental impact. These condensers, constructed using modular components, were installed using large cranes and specialized lifting equipment. The use of air-cooled technology is particularly important in regions with limited water resources, ensuring that the power plant operates sustainably. The Captain Cook Bridge in Brisbane, Australia, completed in 1972, is a significant construction project that spans the Brisbane River, connecting the southern suburbs to the central business district. The bridge's construction involved several innovative engineering techniques and addressed various challenges posed by the river's width and tidal fluctuations. The bridge is a pre-stressed concrete structure consisting of a continuous box girder design. The construction process began with the sinking of deep caissons into the riverbed to provide stable foundations for the bridge piers. These caissons, large cylindrical structures, were constructed using reinforced concrete and driven into the riverbed using pile drive equipment. Once in place, they were filled with concrete to create solid footings for the bridge. The box girder sections were precast in segments on shore and then transported to the construction site using barges. These segments were assembled using the balanced cantilever method, where sections were added symmetrically on either side of the piers. This method ensured that the structure remained balanced and stable throughout the construction process. Each segment was lifted into place using specialized cranes and temporarily supported until the adjacent segments were connected and the concrete joints cured. One of the significant challenges during construction was managing the tidal fluctuations and river traffic. To address this, engineers implemented a detailed construction schedule that accounted for tidal variations and coordinated with local authorities to minimize disruptions to river navigation. Temporary cofferdams were constructed around the piers to provide dry working conditions during low tide, allowing for precise placements of concrete and other materials. The bridge's design also included provisions for seismic activities and thermal expansion. Expansion joints were incorporated into the structure to accommodate temperature variations and prevent cracking. These joints, made of flexible materials, allowed the bridge to expand and contract with changes in temperature without compromising structural integrity. The Red Line Doha Tunnel in Qatar is a key component of the Doha Metro network, designed to provide efficient and reliable public transportation. The construction of this 25-mile-long tunnel, completed in 2019, involved several engineering and logistical challenges, particularly given the region's geological conditions. The tunnel was constructed using tunnel boring machines, which are highly specialized for excavating through the soft rock and soil conditions prevalent in Doha. Each TBM was over 328 feet long and weighed approximately 1,200 tons. These machines were equipped with rotating cutter heads that excavated the soil and rock, which was then transported out of the tunnel using conveyor belts. The construction also involved the careful monitoring and management of ground settlement, particularly in urban areas. Advanced geotechnical instruments such as inclinometers and extensometers were installed to monitor ground movements and ensure the tunnel's stability. This real-time data allowed engineers to adjust construction methods and implement corrective measures as needed, minimizing the impact on existing buildings and infrastructure. The Red Line Doha Tunnel features a dual-track system, allowing for high-frequency train services. The tunnel is equipped with state-of-the-art systems for ventilation, lighting, and emergency evacuation. The ventilation system is designed to maintain air quality and manage smoke in the event of a fire, ensuring passenger safety. The construction process also included the development of underground stations, which required extensive excavation and support systems. These stations were designed with large open spaces to accommodate passenger flow and provide a comfortable environment. The use of advanced structural engineering techniques, such as diaphragm walls and deep foundation piles, ensured the stability and durability of these underground structures. The Red Line Doha Tunnel project showcases the application of advanced tunneling technology and engineering practices to create a modern, efficient, and resilient public transportation system. The project addresses the growing demand for sustainable transportation solutions in Doha, providing a reliable and high-capacity metro network that supports the city's development and connectivity. The Hisingsbron Bridge in Gothenburg, Sweden, a vertical lift bridge, is a remarkable engineering project aimed at replacing the aging Godalv Bridge. Scheduled for completion in 2021, the Hisingsbron Bridge stands out for its innovative design and construction techniques. The bridge spans approximately 1,300 feet and features a vertical lift mechanism, allowing it to accommodate both road and maritime traffic efficiently. The construction began with the installation of deep foundation piles driven into the riverbed to provide a stable base for the bridge piers. These piles were made of high-strength steel and concrete, capable of withstanding the dynamic loads from both the bridge structure and passing ships. This foundation work required precise geotechnical surveys and advanced piling techniques to ensure the stability and longevity of the structure. The bridge's main span is constructed using steel box girders, which are prefabricated off-site and transported to the construction site. These girders were then lifted into place using heavy lift cranes and connected to the piers. The use of prefabrication allowed for high-quality control and reduced on-site construction time. Each girder segment was meticulously aligned and welded to form a continuous structure, ensuring the bridge's strength and durability. One of the unique features of the Hisingsbron Bridge is its vertical lift mechanism, which allows the central span to be raised to a height of 150 feet, providing clearance for maritime traffic. The lifting system consists of counterweights and powerful electric motors, designed to operate smoothly and reliably. The bridge's control system includes advanced sensor and automation technology, allowing for precise and efficient operation. The construction also included the development of approach ramps and road connections, integrating the bridge into Gothenburg's existing transportation network. This required extensive earthworks and the construction of retaining walls and embankments to support the elevated roadways. The approach ramps were designed to provide smooth transitions and minimize disruptions to traffic flow. The Dig-Indy Tunnel System in Indianapolis, United States, is an extensive network of deep rock tunnels designed to reduce sewer overflows into local waterways. Scheduled for completion in 2025, this project involves the construction of over 28 miles of tunnels, each approximately 18 feet in diameter and located 250 feet below ground. The construction process began with the excavation of deep access shafts, providing entry points for tunnel boring machines. These TBMs were specially designed to excavate through the limestone bedrock prevalent in the region. The TBMs, each over 300 feet long, used rotating cutter heads to grind through the rock, creating the tunnel bore. The excavated material was transported out of the tunnel using conveyor belts and hoisted to the surface through the access shafts. The tunnel lining was constructed using precast concrete segments, which were installed by the TBMs as they advanced. These segments, designed to withstand the high pressures at depth, were bolted together to form a watertight lining. The use of precast segments allowed for rapid construction and high-quality control, ensuring the structural integrity of the tunnels. One of the primary engineering challenges was managing groundwater infiltration. The tunnels were designed with a comprehensive dewatering system, including pumps and drainage galleries to control groundwater levels and prevent flooding. Additionally, the tunnel lining included waterproof gaskets and grout injection systems to seal any potential leaks. The Dig-Indy Tunnel System also involved the construction of a large storage and conveyance structures designed to hold and transport combined sewer overflows during heavy rainfall events. These structures were integrated with the existing sewer network, requiring extensive coordination and planning. The project included the installation of advanced control systems, allowing for real-time monitoring and management of these sewer flows. The Dig-Indy Tunnel System project showcases the application of advanced tunneling technology and engineering practices to address critical infrastructure needs. The project significantly reduces sewer overflows, improving water quality and public health in Indianapolis. The construction of this extensive tunnel network demonstrates the capabilities of modern engineering to solve complex urban infrastructure challenges. The Oroville Dam in California, United States, is the tallest dam in the country at 770 feet, underwent significant reconstruction following the spillway failure in 2017. The reconstruction project, completed in 2019, involved extensive engineering and construction efforts to restore the dam's safety and functionality. The reconstruction focused on the main and emergency spillways, both of which were damaged during the 2017 incident. The project began with the demolition of the damaged sections, followed by the excavation and preparation of the foundation. This involved the removal of unstable materials and the installation of drainage systems to manage groundwater and prevent future erosion. The main spillway was reconstructed using high-strength roller-compacted concrete, a technique that involves placing and compacting layers of concrete using heavy rollers. This method provides a durable and erosion-resistant surface capable of withstanding high water flows. The RCC was placed in layers, each approximately 12 inches thick, and compacted to achieve the required density and strength. The emergency spillway was reinforced with a new concrete weir and an extensive network of concrete walls and slabs, designed to control water flow and prevent erosion. The construction of these structures required precise formwork and concrete placement techniques, ensuring that the new spillway could handle extreme flood events. One of the significant challenges during the reconstruction was managing the continued operation of the dam and reservoir. This required careful coordination and planning, including the use of temporary spillways and water management systems to ensure the safety of downstream communities. The project also involved extensive monitoring and testing to verify the performance of the new structures and ensure compliance with regulatory standards. The Oroville Dam Reconstruction Project demonstrates the application of advanced engineering and construction techniques to address critical infrastructure needs. The project restores the dam's safety and functionality, ensuring the reliable management of California's water resources. The successful completion of this complex and challenging project showcases the capabilities of modern civil engineering to solve significant infrastructure challenges. The New Kalani Bridge in Sri Lanka, completed in 2020, is a significant infrastructure project aimed at improving connectivity between Colombo and its suburbs. This 6-lane bridge spans the Kalani River and incorporates several innovative construction techniques to address the challenges posed by the river's width and tidal variations. The construction process began with the installation of deep foundation piles, driven into the riverbed to provide a stable base for the bridge piers. These piles were made of high-strength steel and concrete, capable of withstanding the dynamic loads from both the bridge structure and river currents. The foundation work required precise geotechnical surveys and advanced piling techniques to ensure the stability and longevity of the structure. The bridge's main span, constructed using a steel box girder design, involved the prefabrication of large segments off-site. These segments were transported to the construction site using barges and lifted into place using heavy lift cranes. The use of prefabrication allowed for high-quality control and reduced on-site construction time. Each girder segment was meticulously aligned and welded to form a continuous structure, ensuring the bridge's strength and durability. One of the unique features of the New Kalani Bridge is its cable-stayed design, with cables arranged in a fan configuration. These cables, made of high-strength steel, support the main span and provide additional stability. The cable-stayed design allows for a longer span and reduces the number of piers needed in the river, minimizing environmental impact and improving navigation clearance for river traffic. The construction also included the development of approach ramps and road connections, integrating the bridge into Colombo's existing transportation network. This required extensive earthworks and the construction of retaining walls and embankments to support the elevated roadways. The approach ramps were designed to provide smooth transitions and minimize disruptions to traffic flow. The NorthConnex Tunnel in Sydney, Australia, completed in 2020, is a critical infrastructure project designed to alleviate traffic congestion and improve connectivity between the M1 Pacific Motorway and the M2 Hills Motorway. This 5.6 twin tunnel project involved several innovative engineering techniques and addressed various challenges posed by the urban environment. The construction of the NorthConnex Tunnel began with the excavation of deep access shafts, providing entry points for tunnel boring machines. These machines were specially designed to excavate through the sandstone and shale prevalent in the region. Each TBM, over 470 feet long, used rotating cutter heads to grind through the rock, creating the tunnel bore. The excavated material was transported out of the tunnel using conveyor belts and hoisted to the surface through the access shafts. The tunnel lining was constructed using precast concrete segments, which were installed by the TBMs as they advanced. These segments, designed to withstand the high pressure at depth, were bolted together to form a watertight lining. The use of precast segments allowed for rapid construction and high-quality control, ensuring the structural integrity of the tunnels. One of the primary engineering challenges was managing the ventilation and safety systems required for a long tunnel. The NorthConnex Tunnel features a state-of-the-art ventilation system, including jet fans and exhaust stacks, designed to maintain air quality and manage smoke in the event of a fire. The ventilation system is controlled by an advanced monitoring system, which adjusts airflow based on real-time conditions within the tunnel. The construction also included the development of large portal structures at the tunnel entrances, designed to integrate with the existing road network. These structures required extensive earthworks and construction of retaining walls and embankments to support the elevated roadways. The portal structures were designed to provide smooth transitions and minimize disruptions to traffic flow. The NorthConnex Tunnel project showcases the application of advanced tunneling technology and engineering practices to address critical infrastructure needs. The project significantly reduces traffic congestion, improving travel times and road safety in Sydney. The construction of this extensive tunnel network demonstrates the capabilities of modern engineering to solve complex urban infrastructure challenges. The Tappan Zee Bridge in New York, officially known as the Governor Mario M. Cuomo Bridge, was completed in 2018. This replacement for the original Tappan Zee Bridge required innovative engineering and construction techniques to span the Hudson River and address the demands of modern traffic. The construction began with the installation of deep foundation piles driven into the riverbed to provide a stable base for the bridge piers. These piles, made of high-strength steel and concrete, were driven to depths of over 300 feet to reach bedrock, ensuring stability and durability. The foundation work required precise geotechnical surveys and advanced piling techniques to ensure stability and longevity of the structure. The bridge's main span, constructed using a cable-stayed design, features two 419-foot towers and support the bridge deck with 192 cables. The cable-stayed design allows for longer spans and fewer piers in the river, reducing environmental impact and improving navigational clearance for river traffic. The construction of the towers involved the use of jump forms, which allowed for continuous concrete pouring and ensured structural integrity. The bridge deck was constructed using precast concrete segments, which were transported to the site and lifted into place using specialized cranes. Each segment was precisely aligned and connected to form a continuous deck. The use of precast segments allowed for high-quality control and reduced on-site construction time. The segments were pre-tensioned with high-strength steel cables to enhance the bridge's load-bearing capacity and ensure long-term stability. One of these significant challenges during construction was managing the river's tidal fluctuations and weather conditions. To address this, engineers implemented a detailed construction schedule that accounted for tidal variations and coordinated with local authorities to minimize disruptions to river navigation. Temporary cofferdams were constructed around the piers to provide dry working conditions during low tide, allowing for the precise placement of concrete and other materials. The Tappan Zee Bridge also features advanced safety and monitoring systems. The bridge is equipped with sensors that monitor structural health in real time, providing data on load distribution, temperature, and vibrations. This information is used to ensure the bridge's safety and performance, allowing for timely maintenance and repairs. The construction of the Tappan Zee Bridge demonstrates the application of advanced engineering and construction techniques to create a modern, efficient, and resilient infrastructure asset. The bridge significantly improves traffic flow and connectivity in the Hudson Valley region, addressing the challenges of accommodating both road and river traffic in a densely developed area. Hyperloop One is a groundbreaking transportation project set to revolutionize travel. Conceptualized by Elon Musk and currently under development by Virgin Hyperloop, this project aims to create a high-speed transit system using pods traveling through low-pressure tubes. The technology relies on magnetic levitation to eliminate friction and achieve speeds exceeding 600 miles per hour. Construction involves several critical components: the tube system, the pods, and the stations. The tubes are constructed from steel and reinforced concrete, designed to withstand external pressures and natural disasters. One of the engineering challenges is maintaining a near-vacuum environment inside the tubes to maintain air resistance. This requires advanced sealing techniques and constant monitoring to ensure the integrity of the system. The pods themselves are made from lightweight durable material like carbon fiber and aluminum. They feature aerodynamic designs to reduce drag and increase efficiency. Inside, the pods are equipped with comfortable seating, safety systems, and climate control to ensure a pleasant travel experience. Each pod is designed to be autonomous, with advanced navigation systems to manage speed, direction, and braking. Construction of Hyperloop One includes the development of extensive infrastructure, such as the power supply systems, control centers, and emergency response facilities. The power supply for the Hyperloop is primarily derived from renewable energy sources like solar panels installed along the tube's length. Control centers are crucial for managing the network, monitoring pod positions, tube pressure, and overall system health. In cases of emergencies, the infrastructure includes rapid response teams and safety protocols to ensure passenger safety. One of the major construction challenges is the alignment and leveling of the tubes over long distances. Engineers use GPS technology and laser alignment systems to ensure the tubes are perfectly straight and level. This precision is essential to maintain the high speeds and safety standards of the Hyperloop. Additionally, constructing the system in various terrains, from urban environments to open countryside, requires adaptable construction techniques and materials. The Australia Pacific LNG project is one of the largest and most complex energy projects in the world. Located in Queensland, Australia, this project involves the extraction, processing, and transportation of natural gas from coal seams in the Surat and Bowen basins. The gas is then converted into liquefied natural gas for export to international markets. The project includes three main components: the gas fields, a 530-kilometer gas pipeline, and an LNG processing and export facility on Curtis Island. The construction of the gas fields involves drilling thousands of wells and installing extensive networks of gathering lines and processing facilities. These wells are drilled using advanced drilling techniques to reach deep coal seams and extract the gas. Hydraulic fracturing, or fracking, is employed to enhance gas flow, requiring precise control and monitoring to ensure environmental safety. The 530-kilometer gas pipeline is a critical component, transporting gas from the fields to the LNG facility. Constructing this pipeline involves trenching, welding, and laying pipes across diverse terrains, including forests, rivers, and farmland. Engineers use horizontal directional drilling to install the pipeline beneath major obstacles without disturbing the surface. This technique is particularly useful for crossing rivers and environmentally sensitive areas. The LNG processing facility on Curtis Island is where the gas is cooled to minus 260 degrees Fahrenheit, transforming it into a liquid state for easier transport. This facility comprises liquefaction trains, storage tanks, and loading jetties. Each liquefaction train often involves complex engineering, with compressors, heat exchangers, and cryogenic piping systems working together to cool and liquefy the gas. The storage tanks are massive, double-walled structures designed to safely store the LNG at extremely low temperatures. One of the significant challenges of the Australia-Pacific LNG project is the integration of its various components into a cohesive system. This requires meticulous planning, coordination, and execution to ensure all parts work seamlessly together. Additionally, the project must adhere to strict environmental and safety regulations, necessitating advanced monitoring and control systems to minimize environmental impact and ensure the safety of workers and surrounding communities. Moreover, the logistics of transporting such large volumes of natural gas require sophisticated shipping and handling facilities. The LNG is loaded into specially designed carriers equipped with advanced containment systems to prevent leakage and ensure safety during transit. These carriers transport the LNG to international markets where it's regasified and distributed through local gas networks. The Qatar Metro is an ambitious urban rail project designed to transform public transportation in Qatar. This metro system comprises 4 lines: red, green, gold, and blue, spanning a total of 300 kilometers and including over 100 stations. The construction of Qatar Metro involves advanced tunneling techniques, station construction, and the installation of the state-of-the-art train control systems. Tunneling for the metro lines employs tunnel boring machines, which are large cylindrical machines that excavate and install tunnel segments simultaneously. These machines can operate 24/7, significantly speeding up the construction process. The tunnels are lined with precast concrete segments, which are assembled as the TBM advances. This method ensures the tunnels are structurally sound and resistant to groundwater ingress. Station construction involves creating large underground spaces capable of accommodating thousands of passengers daily. Each station is designed with multiple levels, including concourses, platforms, and service areas. The construction process includes extensive excavation, concrete pouring, and steel reinforcement to create durable, safe, and accessible stations. Additionally, the stations are equipped with advanced safety and ventilation systems to ensure passenger safety and comfort. The train control systems for the Qatar Metro are highly sophisticated, employing automated train operation technology. This system allows for driverless train operation, improving efficiency and reducing the risk of human error. The ATO system is integrated with advanced signaling and communication systems, ensuring smooth and safe train movements throughout the network. One of the significant challenges of the Qatar Metro project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the extreme weather conditions in Qatar, particularly in the high temperatures, require special considerations for worker safety and construction materials. Furthermore, the project includes the development of a comprehensive support infrastructure, such as maintenance depots and control centers, to ensure the long-term operation and maintenance of the metro system. These facilities are equipped with advanced diagnostic and maintenance tools to ensure the reliability and safety of the trains and infrastructure. Patenbam Port in Indonesia is a significant infrastructure project aimed at enhancing the country's maritime trade capacity. Located in West Java, the port includes a container terminal, car terminal, and supporting infrastructure. The construction of Patenbam Port involves a land reclamation, dredging, and construction of extensive port facilities. Land reclamation is the first step, involving the creation of new land by dredging and filling the seabed with sand and rock. This process requires precise engineering to ensure the reclaimed land is stable and suitable for construction. Engineers use advanced geotechnical techniques to compact and reinforce the soil, preventing subsidence and ensuring long-term stability. Dredging is essential for creating deep water channels and berths to accommodate large vessels. This involves removing sediment and rock from the seabed using specialized dredging equipment. The dredged material is carefully managed to minimize environmental impact, and in some cases, it is used for land reclamation. The construction of port facilities includes building quays, warehouses, and support infrastructure. The quays are constructed using reinforced concrete piles, driven deep into the seabed to provide a stable foundation. On top of these piles, concrete decks are cast to create the surface where cargo operations take place. Warehouses and other buildings are constructed using steel frames and prefabricated panels, allowing for rapid assembly and scalability. One of the significant challenges of the Patenbam Port project is managing the environmental impact of dredging and land reclamation. Engineers work closely with environmental experts to implement mitigation measures, such as creating artificial reefs and mangrove restoration projects to preserve marine habitats. Additionally, the project must adhere to strict safety and operational standards to ensure the ports can handle the anticipated increase in maritime traffic. Moreover, the integration of advanced port management systems is crucial for optimizing cargo handling and logistics. These systems include automated cranes, real-time tracking, and inventory management tools to ensure efficient and timely operations. The port's strategic location and state-of-the-art facilities are expected to enhance Indonesia's role in global trade. The Brasilia Digital TV Tower is a landmark structure in Brazil, designed by renowned architect Oscar Niemeyer. The tower stands at 600 feet tall and serves both as broadcast facilities and a tourist attraction. The construction of the tower involves advanced engineering techniques and careful architectural design to ensure its functionality and aesthetic appeal. The tower's foundation is a critical component, requiring deep piles driven into the ground to support the massive structure. These piles are typically made of reinforced concrete, providing the necessary strength and stability. The main structure is composed of a reinforced concrete core, surrounded by steel framework. This combination of materials ensures the tower is both strong and flexible, capable of withstanding wind loads and other environmental forces. One of the unique features of the Brasilia Digital TV Tower is its observation deck, located near the top of the structure. Constructing the deck involves installing large glass panels and steel supports to create a safe and accessible space for visitors. The deck provides panoramic views of the city, making it a popular tourist destination. The tower also houses advanced broadcasting equipment, including antennas and transmitters for digital TV signals. Installing this equipment requires precise engineering and coordination to ensure optimal signal strength and coverage. The equipment is housed in specially designed rooms within the tower, protected from environmental factors and easily accessible for maintenance. In addition to its technical functions, the Brasilia Digital TV Tower is an architectural masterpiece, embodying Niemeyer's vision of fluid organic forms. The construction process required collaboration between engineers and architects to ensure the structure's aesthetic integrity while meeting functional requirements. The tower's sleek modern design is a testament to Brazil's commitment to innovation and progress. The Napoli-Afragola rail station in Italy is a modern transportation hub designed to improve connectivity between Naples and other major Italian cities. The station, designed by architect Zaha Hadid, features a striking architectural design and advanced construction techniques. The station includes multiple levels, extensive platforms, and state-of-the-art passenger facilities. The construction of the station involves extensive earthworks, concrete pouring, and steel reinforcement to create a stable and durable structure. The platforms are designed to accommodate high-speed trains, requiring precise alignment and smooth surfaces to ensure safe and efficient operations. Engineers use advanced surveying and construction techniques to achieve the necessary precision. One of the significant challenges of the Napoli-Afragola rail station project is integrating the new station with existing rail infrastructure. This involves constructing new rail lines, switches, and signaling systems to ensure seamless connections with the existing network. Engineers use advanced computer modeling and simulation tools to plan and optimize the rail connections, minimizing disruptions to existing services. Additionally, the station's design incorporates numerous sustainability features, such as natural lighting, energy-efficient systems, and green spaces. These elements reduce the station's environmental impact and enhance passenger comfort. The station's construction also requires meticulous planning to preserve the surrounding landscape and minimize disruption to local communities. Giga Berlin is Tesla's first European gigafactory, located in Brandenburg, Germany. This massive facility is designed to produce electric vehicles and batteries, significantly expanding Tesla's production capacity. The construction of Giga Berlin involves extensive site preparation, building construction, and the installation of advanced manufacturing equipment. Site preparation includes clearing and leveling the land, as well as installing utility infrastructure such as water, electricity, and sewage systems. This process requires careful planning and execution to ensure the site is ready for construction. The main buildings of Giga Berlin are constructed using prefabricated steel frames and panels, allowing for rapid assembly and scalability. These buildings include production lines, assembly areas, and administrative offices. The construction process involves extensive coordination between various contractors and suppliers to ensure all components are delivered and installed on time. One of the significant challenges of Giga Berlin is the installation of advanced manufacturing equipment. This equipment includes robotic assembly lines, battery production machines, and quality control systems. Installing and calibrating this equipment requires precision engineering and technical expertise to ensure optimal performance. Additionally, Giga Berlin incorporates numerous sustainability features, such as solar panels, rainwater harvesting systems, and energy-efficient HVAC systems. These elements reduce the facility's environmental impact and align with Tesla's commitments to sustainability. The construction also involves extensive collaboration with local authorities and communities to address concerns and ensure compliance with regulations. The Great Man-Made River Project in Libya is one of the largest and most ambitious water supply projects in the world. The project aims to transport water from underground aquifers in the southern desert to the coastal cities in the north. The construction involves digging massive tunnels, laying pipelines, and building pumping stations. The project includes over 1,750 miles of pipeline, making it one of the longest water supply networks in the world. Constructing these pipelines involves extensive excavation, welding, and laying of large diameter pipes. The pipes are made from pre-stressed concrete, reinforced with steel to ensure durability and longevity. One of the significant challenges of the Great Man-Made River Project is managing the environmental impact and ensuring the sustainability of the water supply. Engineers must carefully monitor the aquifers to prevent over-extraction and depletion of the water resources. Additionally, the construction process must adhere to strict environmental regulations to minimize disruptions to the desert ecosystem. Moreover, the project's scale and complexity require advanced construction techniques and materials. The tunnels are constructed using tunnel boring machines, which excavate and reinforce the tunnel walls simultaneously. This method ensures the tunnels are structurally sound and minimizes disruptions to the surface. The pumping stations are equipped with advanced pumps and control systems to manage the water flow and pressure throughout the network. Rail Baltica is a major infrastructure project aimed at integrating the Baltic states into the European rail network. This project involves constructing a new high-speed rail line connecting Estonia, Latvia, and Lithuania with Poland and the rest of Europe. The construction of Rail Baltica includes building new tracks, stations, and supporting infrastructure. Building the new tracks involves extensive earthworks, including excavation, grading, and laying ballast. The tracks are constructed using continuous welded rail, which provides a smoother and more reliable surface for high-speed trains. Engineers use advanced surveying and alignment techniques to ensure the tracks are straight and level, essential for maintaining high speeds and safety. The construction of stations and supporting infrastructure involves creating passenger facilities, platforms, and maintenance yards. These facilities are designed to be modern and accessible, providing a high level of comfort and convenience for passengers. Additionally, the project includes the installation of advanced signaling and communication systems to ensure safe and efficient train operations. One of the significant challenges of Rail Baltica is coordinating construction across multiple countries, each with its own regulations and standards. Engineers and planners must work closely with government authorities and stakeholders in each country to ensure the project meets all requirements and progresses smoothly. Furthermore, the project incorporates numerous sustainability features, such as energy-efficient systems, green infrastructure, and noise reduction measures. These elements reduce the environmental impact of the rail line and enhance the quality of life for communities along the route. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency. The Incheon International Airport expansion in South Korea is a massive project aimed at increasing the airport's capacity and improving passenger services. The expansion includes the construction of a new terminal, additional runways, and supporting infrastructure. The new terminal, Terminal 2, is designed to handle 18 million passengers annually, increasing the airport's total capacity to 72 million passengers. Constructing the new terminal involves extensive earthworks, concrete pouring, and steel erection. The terminal is designed with a modern, open layout featuring large glass windows and high ceilings to create a spacious and welcoming environment. Advanced construction techniques, such as prefabrication and modular construction, are used to speed up the building process and ensure high-quality finishes. The expansion also includes the construction of new runways, which involves extensive earthworks, grading, and paving. The runways are designed to accommodate the largest commercial aircraft, requiring precise engineering to ensure smooth and safe landings and takeoffs. One of the significant challenges of the Incheon International Airport expansion is managing construction activities while keeping the airport operational. Engineers and planners must carefully coordinate construction schedules and activities to minimize disruptions to airport operations and ensure the safety of passengers and workers. Additionally, the expansion incorporates numerous sustainability features such as energy-efficient systems, green roofs, and rainwater harvesting. These elements reduce the environmental impact of the airport and enhance passenger comfort. The construction also involves extensive collaboration with local authorities and communities to address concerns and ensure compliance with regulations. São Paulo Metro Line 4 in Brazil is a critical infrastructure project designed to improve public transportation in the world's largest cities. The new metro line spans over 12 kilometers and includes 11 stations. The construction of Line 4 involves advanced tunneling techniques, station construction, and installation of modern train control systems. Tunneling for the new line employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimize disruptions to the surface. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. The construction of stations involves creating large underground spaces capable of accommodating thousands of passengers daily. Each station is designed with multiple levels, including concourses, platforms, and service areas. The construction process includes extensive excavation, concrete pouring, and steel reinforcement to create durable, safe, and accessible stations. The installation of modern train control systems is essential for the efficient operation of Line 4. These systems include automated train operation tech, which allows for driverless train operation, improving efficiency and reducing the risk of human error. The ATO system is integrated with an advanced signaling and communication system, ensuring smooth and safe train movements throughout the network. One of the significant challenges of the São Paulo Metro Line 4 project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Furthermore, the project includes the development of comprehensive support infrastructure, such as maintenance depots and control centers, to ensure the long-term operation and maintenance of the metro system. These facilities are equipped with advanced diagnostic and maintenance tools to ensure the reliability and safety of the trains and infrastructure. The Central Wan Chai Bypass in Hong Kong is a major infrastructure project designed to improve traffic flow and reduce congestion in the city. The project involves constructing a 4.5-kilometer long highway, including a 3.7-kilometer tunnel connecting Central and Wan Chai. The construction of the bypass involves advanced tunneling techniques, extensive earthworks, and the installation of modern traffic management systems. Tunneling for the bypass employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimize disruptions to the surface. The tunnels are lined with precast concrete segments, providing durable and waterproof structure. The construction of the highway involves extensive earthworks, including excavation, grading, and paving. The highway is designed to accommodate high traffic volumes, requiring precise engineering to ensure smooth and safe traffic flow. Additionally, the project includes the installation of modern traffic management systems such as variable message signs and traffic cameras to monitor and control traffic in real time. One of the significant challenges of the Central Wan Chai Bypass project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Moreover, the bypass incorporates numerous sustainability features, such as noise barriers, green walls, and energy-efficient lighting. These elements reduce the environmental impact of the highway and enhance the quality of life for nearby residents. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency. The Mersey Gateway Bridge in the United Kingdom is a major infrastructure project designed to improve the connectivity and reduce congestion in the Merseyside region. The bridge spans 1.2 kilometers across the River Mersey, providing a new crossing between Runcorn and Widnes. The construction of the bridge involves advanced engineering techniques, extensive earthworks, and the installation of modern traffic management systems. The bridge is a cable-stayed structure, featuring 3 pylons and a series of cables supporting the bridge deck. Constructing the pylons involves driving deep foundations into the riverbed, using reinforced concrete to ensure stability and durability. The cables are made from high-strength steel, capable of supporting the weight of the bridge deck and the traffic it carries. One of the significant challenges of the Mersey Gateway Bridge project is managing construction in a tidal river environment. Engineers must carefully plan and execute construction activities to minimize disruptions to river traffic and ensure the safety of workers and the environment. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. The bridge incorporates numerous sustainability features, such as energy-efficient lighting, stormwater management systems, and green spaces. These elements reduce the environmental impact of the bridge and enhance the quality of life for nearby residents. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency. The Rogfast Tunnel in Norway is a major infrastructure project designed to improve connectivity between the cities of Stavanger and Bergen. The tunnel, once completed, will be the longest and deepest undersea road tunnel in the world, spanning 27 kilometers and reaching depths of 390 meters below sea level. The construction of the Rogfast Tunnel involves advanced tunneling techniques, extensive earthworks, and the installation of modern traffic management systems. Tunneling for the Rogfast project employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimize disruptions to the surface. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. One of the significant challenges of the Rogfast Tunnel project is managing construction in a deep undersea environment. Engineers must carefully plan and execute construction activities to ensure the safety of workers and structural integrity of the tunnel. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Moreover, the tunnel incorporates numerous sustainability features such as energy-efficient lighting, ventilation systems, and emergency response facilities. These elements ensure the safety and comfort of tunnel users and reduce the environmental impact of the project. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency. It's time to talk about the Jakarta-Bandung high-speed rail in Indonesia, which is an ambitious project aimed at significantly reducing travel time between Jakarta and Bandung from over 3 hours to approximately 40 minutes. With an estimated cost of $6 billion, this project is Indonesia's first high-speed rail venture. Construction began in 2016, focused on advanced construction techniques and technologies. One of the primary engineering challenges was the diverse terrain between Jakarta and Bandung, necessitating the construction of numerous bridges and tunnels. The line features 13 tunnels, including the Walini Tunnel, the longest at 4.5 kilometers. The construction of these tunnels employed tunnel boring machines, essential for efficiently and safely excavating through varied geological conditions. The rail line is designed to accommodate speeds up to 250 kilometers per hour, requiring the use of high-strength materials and precision engineering to ensure safety and stability. The tracks are laid on a slab track system, which provides greater durability and requires less maintenance compared to traditional ballast tracks. This system involves laying the rails on concrete slabs to fix in place with high-precision techniques to maintain the alignment and smoothness required for high-speed travel. A significant challenge faced during the construction was minimizing the impact on densely populated areas along the route. To address this, elevated tracks and viaducts were constructed in several sections, reducing the need for land acquisition and minimizing disruptions to local communities. Another critical aspect of the construction process was ensuring the rail line's resilience to seismic activity. Indonesia is located in a seismically active region, so the design incorporates earthquake-resistant features. These include flexible track systems and shock-absorbing materials that can withstand significant ground movement without compromising the rail line's integrity. Logistics played a crucial role in the project's success, given the scale and complexity of the construction. Materials and equipment had to be transported to various construction sites along the 142.3-kilometer route. This required a well-coordinated supply chain and efficient transportation network to ensure timely delivery and minimize delays. Let's move over to Egypt now, where the Grand Egyptian Museum is being constructed. Located near the pyramids of Giza, this $1 billion project covers approximately 120 acres and showcases Egypt's rich cultural heritage through state-of-the-art exhibits and facilities. One of the primary engineering challenges was creating a stable foundation for the massive structure, given the proximity to the pyramids and the potential for archaeological discoveries during excavation. Engineers employed advanced ground-penetrating radar and other non-invasive techniques to survey the site before construction, ensuring that any significant archaeological finds could be documented and preserved. The construction of the Grand Egyptian Museum involved several advanced engineering techniques. The building's foundations required deep excavation and the use of high-strength concrete to support the massive weight of the structure. To address the region's seismic activity, engineers incorporated earthquake-resistant features, such as base isolators and flexible joints, into the design. These features help absorb and dissipate seismic energy, protecting the structure from potential damage during an earthquake. One of the most striking features of the museum is the massive 82-ton statue of Ramses II, which stands in the entrance atrium. Engineers used a specially designed gantry crane and sophisticated system of rollers and supports to transport and position the statue without causing any damage. The sheer size of the project required the coordination of thousands of workers and the management of vast amounts of materials. Engineers employ advanced project management software to monitor progress, allocate resources, and address any issue that arose during construction. Next up, we travel over to the country of Nigeria to talk about the Third Mainland Bridge. Originally opened in 1990, the Third Mainland Bridge spans 11.8 kilometers and is the longest of 3 bridges connecting Lagos Island to the mainland. The expansion and rehabilitation project, costing approximately $300 million, focuses on addressing structural wear and improving traffic flow in one of Africa's most populous cities. Construction commenced in 2018 with a focus on repairing the bridge's deteriorating sections and enhancing its structural integrity. One of the primary engineering challenges was the need to work on a live bridge that supports over 100,000 vehicles daily. To minimize disruptions, the project was executed in phases with specific sections of the bridge closed for repair while traffic was rerouted to alternate routes. This required precise planning and coordination to ensure safety and efficiency. The rehabilitation work involved several advanced engineering techniques. Structural assessments revealed issues with the bridge's expansion joints, bearings, and docking. To address these, engineers employed high-pressure water jets to remove deteriorated concrete and replaced it with high-performance materials that offer greater durability. The expansion joints, critical for accommodating thermal expansion and contraction, were replaced with modern flexible joints designed to withstand heavy traffic loads and environmental conditions. In addition to structural repairs, the project included the installation of new asphalt overlays to improve the road's surface. This involved milling the existing surface to create a suitable base for the new asphalt layers. Engineers use state-of-the-art paving machines to ensure smooth and even surfaces, essential for enhancing driving comfort and reducing wear and tear on vehicles. One of the innovative solutions employed in the project was the use of underwater drones to inspect and repair the bridge's underwater supports. These drones, equipped with high-definition cameras and sonar technology, provided detailed images and data on the condition of the submerged structures. The successful completion of the third mainland bridge expansion is expected to significantly improve traffic flow and safety in Lagos, reducing congestion and travel times for commuters. But what about the International Thermonuclear Experimental Reactor project located in France? Located in Saint-Paul-les-Durance, this international project involves 35 countries and has an estimated cost of around $25 billion. Construction of the project began in 2010, with the project entering the assembly phase in 2020. The reactor is designed to produce 500 megawatts of fusion power from an input of just 50 megawatts, achieving a 10-fold energy gain, which would be groundbreaking of a milestone in fusion technology. The primary construction challenge is the sheer scale and complexity of the reactor components, many of which are being manufactured and assembled for the first time. The core of the project is the tokamak, a donut-shaped vacuum chamber where the fusion reaction occurs. The tokamak must withstand extreme conditions, including temperatures up to 150 million degrees Celsius, 10 times hotter than the core of the Sun. This requires using superconducting magnets to create powerful magnetic fields that confine the hot plasma within the chamber, preventing it from contacting the walls. The construction of these superconducting magnets is a major engineering feat. Each magnet, known as a toroidal field coil, weighs around 360 tons and comprises several kilometers of superconducting cable. These cables are made from a special alloy that becomes superconducting at very low temperatures, maintained by cooling systems using liquid helium. The project also involves constructing numerous supporting facilities, including cryogenic plants, cooling towers, and electrical substations. These facilities are essential for maintaining the reactor's operation and ensuring the safety and stability of the fusion process. One of the key innovations in the project is the use of remote handling systems for maintenance and repairs. Given the extreme conditions inside the tokamak, human access is impossible, necessitating the development of robotic systems capable of performing complex tasks with high precision. These systems are designed to operate in the harsh environment of the reactor, handling radioactive materials and high temperatures. Let's travel over to Australia for the WestConnex project. This $16.8 billion development involves the construction of 33 kilometers of new and upgraded motorways, including tunnels, interchanges, and expressways. One of the significant engineering challenges in the WestConnex project is constructing the extensive tunnel network. The tunnels are built using tunnel boring machines, which can simultaneously excavate and line the tunnels with concrete segments. This method ensures a smooth and efficient construction process, minimizing disruption to the surface environment. The boring machines used in the project are some of the largest in the world, with diameters up to 15.5 meters. Another innovative aspect of the WestConnex project is using smart technology to manage traffic flow and improve safety. The motorways are equipped with an intelligent transport system that includes real-time traffic monitoring, electronic signage, and automated incident detection. This system helps manage congestion and ensures a swift response to any incident, enhancing the overall efficiency of the road network. Measures have been taken to minimize the environmental impact of the construction and operation of the motorways. This includes using low-emission construction equipment, implementing noise barriers and green walls to reduce noise pollution. One of the key benefits of the West Connects project is a significant reduction in travel times for commuters. By providing new and upgraded motorways, the project aims to alleviate congestion for some of Sydney's busiest roads, making it easier and faster for people to travel across the city. It's time to travel over to the United States for the Gilmerton Bridge Replacement Megaproject. The new bridge, costing approximately $134 million, aims to improve traffic flow and safety for the thousands of vehicles and vessels that pass through this corridor daily. Construction of the Gilmerton Bridge replacement began in 2009, with the new bridge opening to traffic in 2013. The new bridge is a vertical lift bridge, which provides several advantages over the old bascule bridge. The vertical lift design allows for a higher clearance for maritime traffic, reducing the number of bridge openings and minimizing delays for both road and river traffic. The new bridge features a vertical clearance of 35 feet when closed and up to 135 feet when fully lifted, accommodating larger vessels that navigate the river. The construction of the bridge includes several advanced engineering techniques. The bridge's foundations were constructed using drilled shafts, which provide greater stability and load-bearing capacity compared to traditional pile foundations. These shafts were drilled deep into the riverbed, and the bridge could support the heavy traffic loads and withstand the harsh environmental conditions of the river. One of the key innovations in the Gilmerton Bridge Replacement Project was the use of precast concrete segments for the bridge's superstructure. These segments were manufactured off-site and transported to the construction site, where they were assembled using a balanced cantilever method. The project also included significant upgrades to the bridge's mechanical and electrical systems. The new bridge is equipped with state-of-the-art lifting machinery and control systems, ensuring reliable and efficient operation. The project included the construction of new pedestrian and bicycle pathways, enhancing accessibility and promoting alternative methods of transportation. Let's investigate the Bogota Metro project next, which is located in Colombia. The first line of this metro development, costing approximately $4.3 billion, will stretch over 24 kilometers and include 16 stations, serving millions of residents in Bogota. Construction of the Bogota Metro began in 2020, with the project expected to be completed by 2028. One of the primary challenges of this project is the dense urban environment in which it began to be constructed. To minimize disruptions to the city, much of the metro line is being built underground, requiring extensive tunneling and excavation work. The use of tunnel boring machines is essential for this task, as they can efficiently and safely excavate the tunnels while minimizing surface disruptions. The metro line is designed to accommodate high-capacity trains that can transport up to 72,000 passengers per hour. One of the innovative aspects of the metro project is the integration of advanced signaling and control systems. The metro will use a communication-based train control system, which allows for real-time monitoring and control of train movements. The construction of the metro also involves significant coordination with existing infrastructure and utilities. Engineers must carefully plan and execute the tunneling and excavation work to avoid disrupting critical services such as water, electricity, and telecommunications. This requires detailed mapping and analysis of the underground environment, as well as the use of advanced construction techniques to ensure the stability and integrity of the surrounding infrastructure. The Bogota Metro is expected to have a transformative impact on the city's transportation system. By providing a reliable and efficient alternative to road transport, the metro will help reduce traffic congestion and travel times for commuters. Next up, we have to move over to Japan for the Azabudai Hills project, located in Tokyo. The project, costing approximately $5.5 billion, covers an area of 8.1 hectares and includes 3 skyscrapers, green spaces, and public facilities. Construction of Azabudai Hills began in 2019, with the project expected to be completed by the end of 2024. One of the primary challenges in this project is the dense urban environment in which it is being built. To minimize disruption to the surrounding area, construction is being carried out in phases, with careful planning and coordination to ensure safety and efficiency. The project features 3 high-rise buildings, with the tallest reaching a height of 330 meters. These buildings will house offices, apartments, hotels, and retail spaces, creating a vibrant mixed-use environment. A key innovation in the Azabudai Hills project is the integration of green spaces and public facilities within the urban environment. The development includes a central park which covers approximately 24,000 square meters and provides a green oasis in the heart of the city. The project also incorporates state-of-the-art sustainability features such as energy-efficient building systems, renewable energy sources, and advanced waste management systems. One of the significant engineering challenges in the Azabadai Hills project is the construction of the underground infrastructure. This includes the creation of underground parking facilities, utility tunnels, and pedestrian networks that connects the various buildings and public spaces. Advanced tunneling and excavation techniques are used to ensure the stability and safety of the underground structures, while minimizing the impact of the surrounding environment. In addition to its architectural and environmental features, Azabadai Hills aims to create a sense of community and connectivity within the urban environment. The development includes a range of public amenities such as schools, healthcare facilities, and community centers, which are designed to meet the needs of residents. It's time to travel over to the country of China. Here, the Shanghai-Nantong Yangtze River Bridge is a major infrastructure project designed to improve connectivity between Shanghai and Nantong. This $3.5 billion bridge spans 11 kilometers across the Yangtze River, making it one of the longest cable-stayed bridges in the world. Construction of the bridge began in 2014, with the project completed in 2020. One of the primary engineering challenges was constructing a bridge that would accommodate both road and rail traffic. The bridge features a dual-use design, with a 6-lane highway on the upper deck and a 4-track railway on the lower deck. This design requires advanced engineering techniques to ensure the bridge's stability and load-bearing capacity. The bridge's main span is 1,092 meters long, supported by 2 towers that reach a height of 325 meters. These towers are among the tallest bridge towers in the world, requiring precise engineering and construction techniques. The towers are constructed using high-strength concrete and reinforced steel to withstand the heavy loads and environmental conditions of the Yangtze River. One of the key innovations in constructing the Shanghai-Nantong Yangtze River Bridge is the use of large-diameter steel cables to support the bridge deck. These cables are made from high-strength steel and can bear the significant weight of the combined road and rail traffic. The cables are anchored in massive concrete blocks on either side of the river, providing the necessary tension to support the bridge deck. The construction of the bridge also involved extensive foundation work, using deep-water drilling techniques to create stable foundations in the riverbed. These foundations are designed to resist the strong currents and seismic activity of the region, ensuring the long-term stability and safety of the bridge. Engineers employed advanced geotechnical analysis and testing to ensure the foundations could withstand the dynamic forces exerted by the river and passing trains. But what about the Cross River Rail project in Australia? This $5.4 billion project involves the construction of a 10.2-kilometer rail line, including a 5.9-kilometer twin tunnel under the Brisbane River in the city centre. Construction of the Cross River Rail began in 2019, with the project expected to be completed by the end of 2024. One of the primary challenges of this project is the need to construct the tunnels beneath a densely populated urban area. To minimize disruption to the city, tunnel boring machines are used to excavate the tunnels. These machines can efficiently and safely bore through the ground while minimizing surface disruptions. The project also includes the construction of 4 new underground stations, which are designed to accommodate high-capacity trains and provide modern, accessible facilities for passengers. The project also involves significant upgrades to existing infrastructure, including track realignment and station enhancements. These upgrades are designed to improve the overall capacity and efficiency of Brisbane's rail network, providing a more reliable and convenient service for passengers. Environmental and social considerations are a key focus of the Cross River Rail project. Measures are being implemented to minimize the environmental impact of the construction and operation of the rail line. By providing a reliable and efficient alternative to road transport, the rail line will help reduce traffic congestion and travel times for commuters. In addition to the construction jobs, the operation and maintenance of the rail line will create long-term employment opportunities, further contributing to economic growth and development. We have to talk about the port of Dum next, which is located in Oman. This $10 billion project covers an area of 2,000 hectares and includes the construction of port facilities, industrial zones, and residential areas. Construction of the Port of Duke began in 2011, with the project expected to be completed by 2025. One of the primary challenges of this project is the remote location, which requires extensive infrastructure development to support the construction and operation of the port. This includes the construction of roads, utilities, and housing for workers, as well as the development of logistics and supply chain networks. The port facilities are designed to accommodate a wide range of vessels, including container ships, oil tankers, and bulk carriers. The construction of the port involves significant dredging and reclamation work to create deep-water berths and turning basins. This requires the use of advanced dredging equipment and techniques to ensure the stability and safety of the port structures. Dredging operations at the Port of Duke utilize cutter suction dredgers and trailing suction hopper dredgers to excavate and transport sediment from the seabed. These dredgers are capable of handling various soil conditions, from soft silt to compacted sand and rock. The construction of the port quay walls and breakwaters involves significant engineering challenges. The quay walls are constructed using precast concrete blocks and steel sheet piles driven deep into the seabed. These structures provide the necessary strength and durability to withstand the forces exerted by large vessels and the harsh marine environment. The quay walls are built using a combination of precast concrete blocks and in-situ concrete casting. The precast blocks are manufactured off-site to ensure quality and consistency, then transported and installed using heavy-duty cranes. The sheet piles are driven into the seabed using hydraulic pile drivers, which provide the necessary force to penetrate the dense seabed material. Let's move over to the United States next, where the Silicon Valley Clean Water Project is located. This $500 million project involves constructing new treatment facilities and rehabilitating existing infrastructure to improve the efficiency and sustainability of the wastewater treatment process. The project includes the construction of a new wastewater treatment plant, which features advanced treatment technologies such as membrane bioreactors and ultraviolet disinfection. Membrane bioreactors are a combination of a biological treatment process and membrane filtration. They offer superior treatment performance compared to conventional methods, providing high-quality effluents by filtering out fine particles and microorganisms. Ultraviolet disinfection is another advanced technology employed by the project. UV disinfection involves exposing treated wastewater to ultraviolet light, which inactivates pathogens and microorganisms by damaging their DNA. This method is highly effective and does not involve the use of chemicals, making it an environmentally friendly alternative to traditional chlorination. This project also involves the rehabilitation of existing infrastructures, including replacing aging pipelines and upgrading pump stations. The pipelines are critical for transporting wastewater to and from the treatment plant. Engineers use trenchless technology such as cured-in-place pipelining to rehabilitate the pipelines without extensive excavation. This method involves inserting a resin-coated liner into the existing pipe and curing it in place, creating a new, durable pipe within the old one. Another critical component of the project is the construction of new storage and equalization tanks. These tanks are designed to manage the flow variations in the wastewater treatment process, ensuring a consistent and controlled flow of wastewater through the treatment plant. The construction of the Silicon Valley Clean Water Project also involves extensive earthworks to prepare the site for new facilities. This includes land grading excavation and soil stabilization. Land grading involves reshaping the land surface to achieve the desired elevations and slopes for the treatment plant. But we haven't talked about the Maputo-Katembe Bridge yet, located in Mozambique. Construction of this bridge began in 2014 and was completed in 2018. One of the primary engineering challenges was constructing a bridge that can span the wide expanse of Maputo Bay while withstanding the region's environmental conditions. The bridge features a main span of 680 meters, supported by two massive towers that rise 137 meters above the water. The construction of the bridge's towers involved using high-strength concrete and reinforced steel. The towers were constructed using slip-form construction techniques, where concrete is continuously poured into a moving formwork that gradually climbs the structure. This method allows for more efficient and continuous construction of tall structures with consistent quality. The towers were designed to withstand strong winds and seismic activity, ensuring the bridge's stability and safety. The bridge's deck is suspended from the towers using large-diameter steel cables. These cables are made from high-strength steel and are capable of bearing significant loads. The cables were fabricated in sections, then transported to the construction site, where they were then assembled and installed using specialized cranes and cable-spanning techniques. The deck itself is composed of precast concrete segments, which were manufactured off-site and then transported and assembled on-site. The construction of the bridge's foundations involved significant geotechnical challenges. The foundations were constructed using large-diameter bored piles, which were drilled deep into the seabed to provide the necessary support for the bridge towers. The piles were reinforced with steel cages and filled with high-strength concrete to ensure their durability and load-bearing capacity. The construction process also included the installation of expansion joints and bearings to accommodate the bridge's movements due to thermal expansion, traffic loads, and seismic activity. The expansion joints are designed to allow for controlled movements of the bridge deck while maintaining a smooth and continuous driving surface. We move over to Australia next for the Shell Prelude FLNG Megaproject. This $12.6 billion project involves constructing a massive floating platform, which is the largest floating structure ever built. The FLNG facility is 488 meters long, 74 meters wide, and weighs approximately 600,000 tons when fully loaded. The hull of the platform was constructed using high-strength steel to withstand the forces exerted by the waves, wind, and currents. The steel plates were fabricated in sections and then assembled onto large blocks, which were transported to the construction site and welded together. One of the key components of the FLNG facility is the topside, which houses the gas processing, liquefaction, and storage equipment. The topside modules were constructed using a modular approach, where each module was fabricated and pre-assembled off-site and then transported to the construction site for installation. The liquefaction process involves cooling the natural gas to minus 162 degrees Celsius, converting it into a liquid form for storage transport. The FLNG facility is equipped with advanced liquefaction technology, including cryogenic heat exchangers and refrigeration units. These systems are designed to operate efficiently and reliably in the challenging offshore environment. The construction of the facility also involved installing subsea infrastructure to connect the platform to the gas fields. This includes installation of subsea walls, flow lines, and risers, which transport the natural gas from the seabed to the platform. One of the key innovations in the project is using dynamic positioning technology to maintain the platform's position without requiring anchoring or mooring lines. The DP system uses thrusters and advanced control algorithms to counteract the forces of wind, waves, and currents, ensuring the platform remains stable and secure. We have to travel over to Singapore next, where the Jurong Island expansion project stands. This multi-billion-dollar project involves extensive land reclamation, construction of industrial facilities, and development of supporting infrastructure. The land reclamation process at Jurong Island uses advanced dredging equipment and techniques to ensure the stability and sustainability of the reclaimed land. Cutter suction dredgers and trailing suction hopper dredgers are used to excavate and transport sand from offshore borough areas to the reclamation site. The dredged material is then pumped into designated areas where it is compacted and stabilized to create a solid foundation for industrial facilities. The construction of industrial facilities at Jurong Island involves significant engineering and logistical challenges. These facilities include refineries, chemical plants, storage tanks, and pipelines, which require extensive planning and coordination to ensure safe and efficient operations. Utility infrastructure is another critical component of the Jurong Island expansion. This includes the installation of water supply and distribution systems, wastewater treatment facilities, and power generation and distribution networks. The water supply system involves constructing desalination plants and reservoirs to provide a reliable source of fresh water to industrial plants and substations to supply electricity to the industrial facilities. The power plants are designed to use natural gas as the primary fuel source, with backup generators to ensure a continuous power supply in case of outages. In addition to the construction of industrial facilities and infrastructure, the Jurong Island expansion also involves the development of supporting facilities such as offices, laboratories, and storage warehouses. These facilities provide the necessary support for the industrial activities and ensure the smooth and efficient operation of the petrochemical hub.